The photon is weird. Sometimes it acts like a wave, sometimes it acts like a particle, and depending on the experiment, sometimes it acts like both. If you're not familiar with the weirdness of a photon, I don't know how YouTube recommended my video to you in the first place. This strange behavior of the photon is what set the foundation for our thinking around quantum mechanics. Also, endless fodder for clickbaity science YouTube videos. So, if we were able to answer once and for all what actually is a photon, then there's a good chance that's going to call into question a lot of our thinking around quantum mechanics. And that is exactly what we are going to do today. In order to resolve this dual nature wavicle that we call a photon, quantum mechanics has had to come up with some crazy ideas to explain the universe around us. And the fact that we have so easily settled on this kind of liminal space between an answer is one of the things that just frustrates me so much. So it has always been my belief that if we could resolve the nature of a photon, we would have a much better way to approach quantum mechanics. Now, if you've seen my videos before, you probably know that I like to set up the evidence and the arguments ahead of time and then kind of bring in my theory. But after going through this script over and over again, I've come to the conclusion that the best way to do this is Columbo style. So, like Columbo, where you see the murder first and you just get to enjoy catching him throughout the show, in this video, I'm just going to tell you what a photon is, and then we will look at all the evidence that supports the thinking on it. So, I hope that sounds good to you. Here we go. So, here's what a photon is. A photon is nothing more than a name that we have given to a set of geometric conditions required for an electron to produce certain interactions in response to an electromagnetic wave. These conditions, while having nothing to do with particles or points in space, can build a new foundation not only for quantum mechanics, but in reevaluating our entire view of the subatomic world. All right, if that all sounded like gobbledygook to you, I apologize. I was trying to create a very scientifically accurate statement. So I'm going to say that again in English. There are no photons. There are only electromagnetic waves. The problem is that when it comes to light, we measure and observe it only through interactions between electromagnetic waves and electrons. And it is those interactions that produce the particle-like behavior, having nothing to do with the actual nature of what light is. I'm going to prove this to you, so just hang on. The other thing that many people who watch my video know is I like to be very careful to separate between what I am telling you that is accepted science and what I am telling you that is my own theory. However, and this is where it gets really tricky, in this video, everything I'm about to tell you is accepted science. The only thing that's my theory is the thing I just told you. And so you're going to get to the end of this video probably asking yourself, well, Chris, if we already know all this and this is the way it is, why don't we think that this is what a photon is? Well, I've been asking myself that this whole time. So to begin, let me explain to you what electromagnetic waves are and how they work. We are going to focus on the E in EM. So electromagnetic waves, we're focusing on the electro part. It just makes the mechanics much more simple. Also, when we're talking about light, the magnetic component almost never comes into it anyway. We will get to the magnetic part in a later video. You start with a source of an electric field. In this case, we're going to focus on the electron. The electron creates a negative electric field. When that electron moves, however how small it moves, the entire field around it now has to update. So this is how it works. When we show the electron, and it's just sitting there, We represent the electric field it creates through vectors, lines and arrows that we draw pointing towards it. These lines are arbitrary, by the way. They could be pointing away from it. We just had to pick a direction for negative and a direction for positive. Just keep that in mind. So the electron is producing this electric field. The vector lines are all pointing at it. That represents the state of it throughout the whole universe. When that electron moves, the entire electric field has to update. As we know, in this universe, information cannot move faster than the speed of c, the speed of what we call the speed of light. So when an electron moves, this update in the electric field starts from the new position of the electron, and it expands outward in a sphere at the speed of c. This update is the EM wave. That's what's waving. It is an update of information. Now, the boundary of this update, what forms the surface of this expanding sphere, is what we call the kink. That's right, electromagnetic waves are kinky. As we know, kinks can be attractive or repulsive. Yeah. So when this update hits another source of electric charge, then that source is going to have to move, if at all possible. So as we know, like charges repel, opposites attract. Not always the way with kinks, but in this case. So as the electric field changes, any other electrons in that field will now move to, again, be as far away from each other as they possibly can. Okay, now this forms the foundation of what an EM wave is. However, when talking about light waves, one kink is not enough. In order to get a light wave, we need a series of kinks. The electron can't just move. It has to undulate, moving back and forth in rhythmic sequence. Oh, come on.
What? You said undulate. That's basically worse than moist. Not to mention you back and forth in a rhythmic sequence.
Okay, fair. That's my bad. For any given distance, an electron travels back and forth. You get both frequency and wavelength according to how fast it travels over a certain distance. Within the same distance, an electron traveling faster than another will produce an EM wave at a higher frequency and a shorter wavelength, while an electron traveling the same distance at a slower rate produces a lower frequency and a longer wavelength. If the distances are the same, then the high frequency and the shorter wavelength is an indication of more energy. However, with different distances, you can have the same amount of energy translated into different frequencies and wavelengths. This is because two electrons with the exact same momentum will travel back and forth at different rates if the distances are not the same. Some of you out there might realize that I also just explained a good chunk of how radio waves work. That's because radio waves and light waves are both EM waves. In this case, I am just ignoring the magnetic component for the sake of simplicity. I want to stop for a minute and just point out that having this basic understanding of what an EM wave is so critical. Understanding that an EM wave is comprised of this information update. The fact that the universe just can't update instantly when a source of electrical charge changes. That update has to radiate out. Once that clicks, it really helps everything fall into place. It's the motion, though, that gives us the frequency, the wavelength, and the patterns that give us all the other things then, like light and radio waves. This is the wave, so what makes light look like a particle? So now we get to the photon. At what point does an EM wave go from being a spherical expanding structure to being a point, right? And that's the whole point. We think a photon is both a wave and a particle because we detect it at points. But this point where we detect a photon is actually more of a rectangle. There is no point at all. What we call a photon is just a set of circumstances that produce this detection event. So what I'm going to do is describe to you those circumstances. Number one, an EM wave is emitted by an electron, no duh. But the key is that the vast majority of the time, this is done by an electron that is atomically bound, meaning an electron orbiting the nucleus of an atom. Okay, that's one. Number two, the EM wave must contain a full sine wave of motion to produce a frequency and a wavelength, aka oscillating motion. Oscillating. Number three, another electron must be in the path of the emitted EM wave in order to detect it as light. Number four, the detecting electron has to be free to move parallel to the emitting electron. Number five, the detecting electron's parallel motion, or dipole moment if you want to hold your pinky out, must be perpendicular to the direction of the expanding wave. If you're having trouble following this, we are illustrating it, so stop listening and watch the video. Now, those are a lot of conditions, so let me simplify this for you. To do this, I'm going to refer to what is probably the best video on light waves on the internet right now by 3 Blue 1 Brown. I seriously recommend watching this video in its entirety after this one. Heck, you could even pause right now and just go watch that one and come back to this. It'll just help everything make a lot more sense. They coincidentally released this video while I was working on this script and have saved me a whole lot of time in production and 3D animation.
No, saved me a lot of time on 3D rendering and animation.
Sorry, saved my editor a lot of time on production and 3D animation. First, you can see that when an electron moves, the change in the EM field produces a full expanding sphere of changing field vectors. You could also see that those vectors are most significant in a ring around the center where they are parallel to the electron's motion. You can also see in this clip that the emitting and receiving electrons are moving parallel to each other. Their electrons don't have as much personality as ours, but we'll let that go. And here you can see the emitting and receiving electrons' oscillation is perpendicular to the expansion of the wave. There you can see with your own eyes all the conditions required to go from an EM wave to producing the interactions that we currently call photons. Because light waves are emitted by electrons and detected by electrons, the point-like interactions we have mistaken for a particle are actually just discrete events from the electrons. And there you have it. There is no need for wave-particle duality or wavicles. It's just EM waves producing discrete events. But I have one more thing.
One other thing.
Those animations I showed don't really prove my second condition that I described, that the emitted electron must produce a full wave of motion. How do we know that's true? Well, that is implicit in the very equation of a photon. As you can see, we either use the frequency or the wavelength of light to deduce its energy. You can't have frequency and wavelength without oscillation. Okay, now you math heads might be yelling at the screen because you know, well, I can use math to take even the slightest sliver on a graph and deduce or extrapolate a full sine wave. But it doesn't mean it's physically there. The electron can't do math. It can only respond to physical changes. So if it is going to respond to a light wave and produce its own EM wave, it has to physically move. It can't just do math. I will die on this hill. There is nothing wrong with using logic and reasoning in science. Math should be for describing our reality, for verifying assumptions, but not for creating reality, okay? In this case, the nature of physical oscillation is absolutely implicit in the observed measurement and observations of light. Again, we know this because of radio waves. Radio waves are also EM waves. The biggest difference is that while light is typically produced by again, atomically bound electrons. Radio waves are produced by pushing and pulling electrons up and down through a conductive medium. That's why the amplitude of radio waves are very large and the amplitude of light waves are very small. Okay, but if you're still not happy with that as an explanation as to why an electron requires a full sine wave of motion, just because of the equation that we've observed, just because of the math, or any of these other things, there's two other very good reasons why we should assume this to be true. First is an electron orbits the nucleus of an atom. It's hard to orbit something without a full circle. I realize that our kind of primitive solar system model of the atom is not accurate, that electrons kind of inhabit more of this probability cloud. But it doesn't take away from the fact that they still are around the nucleus of an atom. But even more so, there's the fact that, and this is really cool, waves have inertia. If you've never thought about it before, it sounds counterintuitive. When we think of something having inertia flying through space in a vacuum, it makes sense for it to go in a straight line until something stops it. It's very easy to get your head around something spinning and continuing to spin in space. But the truth is waves also have inertia. And that is because waves are comprised of vectors and circles. A wave in the end is a complete circle. A sine wave is a full 360 degrees. And it is required for that inertia to be communicated from one thing to another to complete the full sine wave in order for that inertia to take place. Otherwise, what you are going to communicate to the other object is not going to be a wave. And that is the best evidence we have to know that if we're talking about a wave communicating its information to another object, that information has to be completed through a full sine wave of motion. So an electron can only re-emit a full sine wave of motion if it received a full sine wave of motion. Okay, but one more thing.
One more thing.
I said before, the shape of a photon is more like a rectangle. So now, if you put everything together that we just talked about, the shape of what we call a photon fits more accurately within something like this. Because on this card here, I have a full sine wave represented. And what we now know is that this wave has to pass by the electron completely from beginning to end in order for it to communicate the wave. So that means we have our height, the width, I'm going to put a big asterisk on, we'll get back to that later. But that's basically it. That's the area that creates an effect that we call a photon. It's a rectangle. Now, here's where we get to the really cool part. And this is where the evidence for this occurring starts showing up in all of the math and all the experiments that we have when it comes to photons. And that is the concept of a projected plane. So here's how a projected plane works. So this card I'm showing you right here, if I'm holding it perfectly straight at the camera, you can see that it's 2.5 inches by 3.5 inches. And we're going to call it card 0, okay? That is the plane of the card, but it's also right now the projected plane. In other words, this is in 3D space right now. And if I hold it like this, the area that you see is the area that matches perfectly with the physical dimensions of the card. However, if I turn the card a bit, now the projected plane, the surface area of the card that you see, is less. So the equation to now understand what the area of this projected plane is to you is we have our new plane, card 1, is equal to card 0 times cosine squared 45, 45 being the angle of which now I have tilted the card. I'm going to take card 0 and I'm going to multiply it by cosine 45. The area now of the projected plane is 4.375 square inches, okay? And again, it's called projected because I'm taking this from a 3D world and I'm limiting it down to your 2D world on your YouTube screen. Okay, now, let's say we're talking about this card, again, representing the sinusoidal EM wave from our emitting electron. In this case, we're showing just one card equaling one wavelength. Now remember that in the case of light, we can't have just any wavelength, because the other part of the equation here shows that we have to have a wavelength that falls into a certain quanta, which, extremely small quantity, in this case, the Planck length. That's what the H means. This is both the term and the concept that quantum mechanics is founded on. So to understand this H in our equations, what you need to do is you need to think of the C as like a ruler. That's the full length of our ruler. And the H is notches in that ruler. So this means our wavelength needs to be able to go from one notch to another notch. It has to meet in those small, tiny increments. But if I were to take that same wavelength and now tilt it just a little bit, there's a good chance now that I am falling not on those notches, but between them. Due to the nature of an atomically bound electron, something which I can't dive into yet in this video, it is impossible to produce a non-quanta of an EM wave. All the waves it produces have to fall within this predefined quanta of wavelength. However, in free space, I can take this quanta-constrained wave, which I'm representing with the card, and I can tilt it just a little. So even though my playing card may obey the rules, the emitted electron produced a quantum bound or a quanta increment of a light wave. In free space, I can twist that a little bit. So that creates a problem. And that problem is that an electron is basically a point in space. It's very small, itty bitty teeny tiny. We have estimates of how big an electron is, but we don't really know. Its size is completely theoretical at this point because it's too small for us to measure. So all this is to say that this wave emitted from one electron going to another pretty much has to be communicated within line of sight of one electron to another. In other words, it's really impossible to graze an electron. So that's why they have to be lined up so perfectly. What that leaves us with, going back to our kind of, thinking about the pictures we painted at the beginning of an electron moving and producing an entire expanding sphere of change to the electric field, we are left with a ring around the sphere that is parallel to the emitting electron that can communicate light from one electron to another. That's right, photons are rings. Now, hold on, that's true. Around every emitting electron, every electron that emits a light wave, there is a ring of potential photons. And I use that term with big scare quotes, okay? It sounds absolutely weird. We've never been taught that. But if you look at the 3D models that the math produces, like in 3 blue, 1 brown, you look at the equations that we have for expanding EM waves, it's all there. It's just, I don't know, even though we can literally 3D model it and see it right in front of us, we don't see it. But the truth is, light waves are rings. I mean, they're spheres, but the area ring around the emitting electron as it expands is the place where another electron can be stimulated and re-emit another wave. I gotta say, this realization was probably my favorite part of this whole project. The fact that when we're talking about one electron, and we'll talk about why it's only one in a minute, oscillating produces a ring of potential photons. Once that sinks in, it is amazing how many things that affects. And we're going to go through it in light, in optics, even in what we call entanglement. All of these things start having an underlying intuitive explanation just with that understanding. And by the way, I will give credit. My editor was the first person to figure that out. If an emitting electron produces a ring of potential photons, why don't we ever experience that? Well, that's for several reasons. The first one is because the only way you would experience that is for that ring to hit 2 electrons at the same time. And given the conditions we just talked about, that's incredibly hard. But it does happen, and we'll get to that later. The other reason is because as this ring expands, most of the stuff in our world isn't arranged like that. You know, it's hitting flat or jagged surfaces. So as that ring expands and hits, like, let's say, a flat surface, it's going to hit at different times depending on where the ring is. But finally, the biggest reason why we seldom observe a light wave as a ring is because we mostly observe light in streams. And this is the other critical thing for you to get to understand light. When you hear science YouTubers, like the chart we showed, or the thumbnails that we showed before, talk about light, you will notice that they are very careless to confuse the idea of a single photon with lots of photons. And it is a big difference. Beams of light, as we know them, like lasers, or when we're doing experiments with refraction, what we think of as light going in a straight line isn't a photon going in a straight line. It's lots of photons that produce a coherent wave in a line. And again, I'm going to refer back to the 3 blue, 1 brown video. As you can see here, if you align the oscillating electrons up, one next to the other, the waves along the sides cancel each other out. And now you get more or less a coherent wave going out from the front and the back of those electrons. And this is the majority of the way we experience light. Lasers, flashlights, TV screens, I mean, you name it. The only time we really don't experience light like that is with a good old-fashioned classic light bulb just sticking out of a socket. It's easy for us to think of light going in a straight line because most of the time we experience it, it is. But where this gets troublesome is when we confuse in our experiments a stream of light with the idea of a single photon. And we will cover that here as we go. So to end this section, here's the bottom line.
Bottom line? The bottom line.
When we're talking about the idea of light from the perspective of a single electron, light is not a particle. It exists basically in 2 main ways, depending on how you look at it. In a single photon form, it is a ring. An oscillating electron produces a ring of potential photon interactions. But when we're looking at a single photon interaction from one electron to another, we are looking at a rectangle where all the conditions required for one electron to stimulate another is contained in this rectangle. And this rectangle is basically stacked around like a ring around the emitting electron. Now that you have that idea of what light really is and what photons, which don't exist, are actually, which are just, again, interactions, now we're going to take a look at many of the big experiments that we use to observe this wave-particle duality, and you will see this simple physical explanation fall into place consistently across all of them. All right, so now we're going to talk about the first legendary experiment that made us think of light as a particle, and that is the photoelectric effect. This is the thing Albert Einstein actually won the Nobel Prize for. Surprisingly, not general relativity. It was this. So the photoelectric effect was a continuation of work by Max Planck, by which we get the Planck length from, around observing black body radiation. These works mark the birth of the ideas behind quantum mechanics in the early 1900s. Einstein's paper on this was published in 1905. The photoelectric effect is an explanation for 2 main observations. So first of all, that when shining light at a metal surface, electrons were ejected from that surface when light exceeded a certain minimum frequency. No matter how intense the light was, no matter how much light was shown at it, The only thing that influenced how many electrons were kind of kicked off of that metal surface was the frequency of the light. And this was a little surprising to us because we figured the more intense the light or the more light there is, the more energy there must be, but it was only the frequency that mattered. The kinetic energy of the ejected electron also depended only on the frequency of light, not the intensity. In other words, the higher frequency of light transmitted, the more energy to the receiving electrons, and the intensity of light made no difference. So the two big things that came out of this experiment was, again, this idea that light is both a wave and a particle, but also this idea of quanta of energy. And, this is where we got our original equations for energy of a photon, which we've been using through this script. The real reason that we got the idea that light must be a particle from this experiment was because when we observed light knocking off electrons on our surfaces, it only happened at certain points. So it wasn't spread out, consistent. It was happening at points on the display. And that doesn't make sense. If it's a wave, the whole wave should influence the metal surface. Why is it happening at specific points? It must be a particle. But now that you understand that the wave of light emitted from an electron can only affect another electron under certain conditions, now we know why we observed light in points. And to drive home this point, I want to show you an experiment done by Action Lab here on YouTube. Now, he's using an electroscope to show the photoelectric effect, and ironically, he's using this video to show why light is made of particles, but we're going to explain it a bit differently. Now, basically the way this works is he has a plate on top that gets charged. He's using static electricity to charge it, and he has an indicator in the circle that is repelled from the plate as it gets charged. Now, first thing I want you to notice is that when he touches the plate with his finger, the charge or the extra electrons move from the plate to his finger almost instantaneously. It happens very, very quickly. But as this video goes on, and he shows the difference here between how intensity doesn't do much, and he switches to his high frequency light to now show that the high frequency is ejecting electrons, the thing I want you to notice is how long it takes for light to eject those electrons. We know they can move quickly because he did it with his finger, but when he's using the light, it happens very slowly. And this is because interactions between light and electrons works like a lottery. It takes, we're talking countless photons being sent out so that we get lucky and have a few of those match up perfectly with the electrons so that the energy is communicated and the electrons are ejected. So the reason we see these point-like interactions isn't because it's not waves. It's because the conditions for the waves to line up with the electrons just right is so strict that it happens so infrequently compared to the amount of photons that we are shooting off. So after the photoelectric effect experiment, caused a ruckus, there soon came another experiment closely following it that really sealed the fate of us thinking of light as both a wave and a particle, and that is Compton scattering. So this experiment, which took place about 1923, was done by Arthur Compton, so hence Compton scattering. And basically, we take X-rays and shoot them at a graphite surface. Now, what they observed is that for electrons that were loosely bound to the atom, the high energy X-rays, which we're still calling light, those are light too. Again, they're all light. So the high frequency X-rays would hit these electrons in the graphite, unbinding the electrons, so knocking them off, and then the light would go in the other direction, and they would kind of go in a symmetrical split up to about 180 degrees. What they observed is that the smaller the angle of the split, the less the frequency of light was diminished. But as the angle increased, going all the way up to 180 degrees, with the electron going one way and light going completely the other way, we had the biggest change or decrease in frequency of the emitted light. Now, in trying to figure out why this occurred, Compton went back to the equations Einstein had from the photoelectric effect, which assumed light was a particle. And he brought those into his math to show why this was occurring. Now, this is one of first of many rabbit holes that we're going to have in this video. I actually intend to do a mini follow-up video just on this experiment so we can take a detailed walkthrough of the math and kind of where we went wrong. The bottom line is this all comes down to special relativity, a principle which I covered in my previous video expanding on the idea of the light compass. But basically, if you have an electron that starts oscillating, but then gets shot out of the atom, and so it's going one way, but still oscillating, then you have EM waves being generated now producing a stream angle on the other side. Those are basically just going to be redshifted. There is going to be a kind of a stretching out relatively of the frequency of light. It's perfectly normal. It makes perfect sense. It's just special relativity and light waves. There's no reason for a particle in this experiment. So the biggest problem with the Compton scattering experiment isn't just that it sealed the fate of us thinking of a photon as a particle instead of wave, but that it contains a logical error that has persisted for almost 100 years that has caused us to misinterpret quantum interactions and fail to understand other things that we observe, some of which we'll get to later. That logical error is assuming that what we observe in a stream of photons is perfectly applicable to a single photon-electron interaction. So, as we showed you before, when you have many electrons next to each other or together oscillating, that is what gives directionality to light, because the sides cancel out, and now you have a stream in one direction. When the X-rays hit the graphite, it is a stream of X-rays, it is ejecting a stream of electrons, and for a brief moment of time, as the electrons are ejected from the graphite, they are still oscillating, producing a coherent stream of light in a direction. But if we were able to run this experiment, ejecting only one electron at a time, we would find that the photon detection is unpredictable. And that, by the way, my friends, is what we call falsifiability. And I'm hoping someone with a little more money and time tries to run that experiment. All right, so the more interesting experiment, and certainly the one that takes up more time here on YouTube and catches more science journalism headlines, is the famous double-slit experiment. So for those of you who don't know what the double-slit experiment is, again, I'm not sure how you found this video in the first place, because you had to have watched it like half a dozen times before this one. But anyways, let's just do a quick review. Feel free to fast forward if you already know this. So in this experiment, we take a coherent light source. The point is it's usually a laser. So we take this laser and we shoot it through a barrier that has two slits in it. Now these slits, in order to work, the size and spacing of these slits have to be related to the wavelength of the light that's actually going through them, or you don't get quite the effect that you want. A screen is placed on the other side of that slit, and if we did this right, we should get an interference pattern on the screen. And this is the thing that helped us reinforce that light is still a wave. Because even though we're still detecting points of light on that screen, all those points add up to basically these lines where we can see a interference pattern like a wave. Again, if you have no idea what this experiment is, there's plenty of other YouTube videos that go into it in more depth. Just a quick review. So the observations from this experiment are as follows. First of all, when just shining the laser through the two slits, we see an interference pattern, which makes us think light is a wave. What's even weirder is that if we shoot one photon through at a time, and then we add up where those photons hit over time, we still get an interference pattern, making it look like one photon is interfering with itself, which is weird if light's a particle. But even weirder with the double-slit experiment is that if we try to observe which slit the photon goes through, the wave interference pattern collapses or goes away, which is spooky because it makes us think that by observing reality, we change it. Okay, so let's explain all of this real quick now. So first of all, the fact that light interferes with itself, that's fine because light is a wave. We've established that light is a wave. Even one photon, again, one photon going through at a time is still an entire wave passing through both slits. The reason we only detect it at one point is the reasons that we went through before. But the thing that boggles everyone's brain is, why is it when we try to observe which slit the photon's going through, does the interference pattern disappear? That's the one that makes everyone go, ooh, okay? So let's just address that one flat out. When scientists say we are observing which slit a photon goes through, they are lying. We observe jack shit. As we know, all the way back from the photoelectric effect, we don't observe photons directly. We only observe light through its interaction with other electrons. And we have an electron emitting light, we have electron re-emitting light, we have our eyes, which detect light with electrons. We never actually see the things anyway. What we're just getting is the electrons. So that's where our points are coming from. So we're not watching a photon pass through a slit. We can't. It's impossible. The word observe makes it sound like we're watching as the photon passes through a slit, but we can't. We can't. We see nothing. All we can do is wait until that wave hits another electron. Oh, Chris, but what if we built a detector? Well, guess what a detector is? An electron. It's something that the light can stimulate. And here's the problem. If you have something that is stimulated by an EM wave, what happens is that you create another EM wave. Now, this is the experiment when I originally started doing this chapter that I wanted to set up and show. Thankfully, we actually found someone else already did this experiment, and I have a link to it in the description of the video. So it turns out in 2010, Applied Physics Letters published a paper where the authors created an experiment to try and shed light on the double-slit experiment. Now, just as a side note, for this experiment, they used electrons, not photons. But I want to note that difference. But the result still proves the point, so bear with me. They created a version of the experiment that used a low atomic number material, so that means really, really thin, to detect if a particle passed through one side with the hope of leaving the electron as it passed through unaffected. However, even with this super thin material, they found that while the particles passing through the open slit, so the one where we're not detecting it, produce what we call elastic scattering, basically meaning that it behaved like a wave passing through an opening in a barrier, while the detecting slit produced inelastic scattering, which basically means a new wave starting from scratch. And the best way I can describe the difference between the two is just show you this picture. The bottom line is one of these is the wave as it passes through the barrier, and the other one is a brand new wave. Now, they don't make the following conclusion in this paper, but you can see that with everything we have explained about EM so far, it is impossible to detect them without changing them or making new ones. In other words, the problem with using the word observe when talking about photons is that you can't observe them without messing with them. In fact, you can't observe anything in the quantum world at all without interfering with it. And most of the time, we are observing quantum objects. It is done by shooting them with a laser. That would be like observing the position of runners in a marathon by pelting them with rubber bullets and measuring the angle they bounce off. Gee, I wonder why measuring them makes them change position and velocity. Must be that observation changes reality. Of course you change reality when you shoot shit at it. That's how reality works, you pretentious morons. The point here, light produces an interference pattern because it's an electromagnetic wave. When you push a wave through two slits, you get two wave patterns. Those patterns can interfere with each other and produce an interference pattern because they're waves. If you instead block one of the slits and instead create a new EM wave, which is what's really happening when we try to detect them, then the chance of them interfering is very small, and they certainly won't produce a consistent pattern because now they're two completely different wave patterns. But let's not stop here. The double-slit experiment has spawned a variety of spin-offs that have provided what are up until now similarly mind-blowing and confuzzling results. So as I mentioned before, we also have the single photon experiment, where it's just one photon at a time going through the double slits, and it still produces an interference pattern when we add up all the detections over time. And again, of course it does, it's a wave. But here's the other problem I wanted to point out with this, and that's the phrase, a single photon. And here's where I want to elaborate on this a bit. There is no universal definition for what a single photon is. A single photon is kind of determined by the experiment. For example, during the photoelectric effect, a single photon was described as however much energy it took to eject an electron. In other experiments, it's based on just what's the lowest amount of energy we can detect a photon. See, here's the thing we're not quite sure about. When I say it takes a full sine wave of motion to produce a photon, we don't know if it's just 1 or 2 or 3. Depending on the experiment, this thing could be 3 meters long. We don't know. The smallest a photon can be is 1 sine wave. And I'm skeptical, although it certainly might be possible, that we've ever had an experiment that confirms 1 sine wave of detection. So just a little clarification for you guys too when you're playing at home. Now, on that note, that brings us to the next crazy double-slit experiment. You guys may have seen somewhat recently the headlines about this idea of a time-slit photon experiment. So this is the idea that instead of sending a photon through slits, we just create these basically attosecond, very, very tiny bursts of light. And we shoot them in a straight line. And to our amazement, we still get an interference pattern. So I have references to these experiments in the description. You can go and look for them, at them for yourself. Now, the fact that shooting these small amounts of light, one after another in a straight line, producing an interference pattern, led to the headlines, photons interfere with themselves backwards through time. Oh, no, they just interfere through space because they're waves. This is very simple to deduce. If I take water and I just drop little drops of water in a row, you see that as the waves expand, they interfere with each other. It's completely understandable why this would happen. They don't need to be traveling backwards through time. Now, some of you, if you're really paying attention, might notice, though, there is one small problem with this analogy of water droplets I'm using for the light, but I'm going to wait and see how many of you catch it and cover it in the follow-up video. The point here is that all these interference experiments and their spin-offs are all easily rationalized and explained once you understand that what we call a photon, again, is just a small area of interaction with geometric requirements of an expanding spherical EM wave. But to really pull the quantum nuttiness out of photons, we got to dig out the whole root So let's talk about polarization. So we are going to discuss a few observations around photons and polarizations, but first let me explain what polarization is and how it works. Going back to our playing card right here, the direction of the y-axis is the direction of polarization. So if this were coming at you, this is the polarization, up and down, side to side. So this direction of oscillation that electron is moving is technically called the dipole moment. It just means it wiggles back and forth on that axis, but scientists love to come up with esoteric terminology for things. There are three ways light can be polarized. So it can be polarized vertically, it can be polarized horizontally, or it can be spinning. So circular polarized light, or it can be unpolarized. We won't get into that right now. That just basically means it's a ton of photon. No, light is always polarized individually. When you just get a ton of them together, they all kind of average out, and we call that unpolarized. Sorry to give you the whole background of polarization, just bear with me, this will be important. One of the little experiments that get a lot of attention on YouTube here is the 3 stacked polarizers. With the context of our new understanding of light, I'm going to revisit this for 2 reasons. One, it further drives home the nature of light as a wave, and a photon is just a geometrically conditioned interaction. And number 2, the true nature of polarization has a lot of ramifications for quantum mechanics. So let's talk about the 3 polarizers. What happens is we shine light through one polarizer, and it only allows light that is oscillating at a certain direction, so that's our polarization, to pass through. So if I have sunglasses, they may only let horizontal polarized light through, or they may only let vertical polarized light through. That's how we get less light through sunglasses. But if we take that now and we add a second polarizer oriented 90 degrees to the first one, then that is going to block out all the light, because one of them blocked out everything horizontal, the other one blocked out everything vertical. But if we add a third polarizer between them at 45 degrees, the really weird thing is that we actually end up getting more light through than with the 2. And that doesn't make sense when you think of light as a particle, because if you have 2 filters that filter out 100%, adding a third filter should filter out more. So what's going on? But again, this is only confusing if you think light is a particle. If you think light are waves, it's very easy to explain the whole thing. So first of all, what you need to understand is that these kind of polarizers that we're talking about here, they work by having a material where the atoms are so close together on one axis and farther away on another that it basically constrains the electrons and forces them to move along only one axis. The direction the electrons are free to move, again, the dipole moment, is the direction in which the polarizers will polarize light. If we go back to our photon card analogy, the direction of oscillation of the sine wave, again, now has to match the axis of the electron in our polarizer where it's free to move in order to perpetuate the wave. That's the key to understanding this whole thing. Polarizers aren't actually filtering light at all. They are producing new light waves based on how they are stimulated. None of the original waves actually pass through the polarizer. Their energy is transferred from the waves that hit the polarizer to the electrons in the polarizer, and this is all according to an equation that we've had around for a very long time now called Malice's law. And we'll explain the math of that in a minute, but first let me just drive home the mechanics of how this works. The light which matches the polarizer will stimulate a new wave pretty much the exact same intensity as the one that hit it. But the light perpendicular to the polarizer is just turned into heat. And the light that is in the middle kind of does both. Half of it is turned into more light and half of it is turned into heat. And the way this works, and we're going to go back to our cards again, is think about if I take this card and I throw it through a slit. If that slit is aligned to the same axis as the edge of the card will go right through without any energy loss. If I throw the card at the slit and the axes are misaligned, the card may still go through, but the energy is lost to the friction and the collision of the sides of the card and the surface. Lastly, if I throw the card at the slit where the axis is completely perpendicular, it won't go through at all. It'll just hit and fall off. The purpose of this analogy is to show you why the effect of light on a polarizer, and many other circumstances in fact, follows that of a projected plane, which we talked about before. However, instead of the plane being calculated by how flat it is compared to your view, in this case, it's calculated by how aligned the wave is to the dipole moment of the electron. So in other words, when we're looking at the electron's point of view, this would be 100% of the energy, and this is where we start getting lost. So it works like this, and now we'll get into the math of Malice's law here. So for the first polarizer, let's say the initial light source has an intensity of, we're going to just call it I0, okay, or I0, and it is unpolarized light. After the first polarizer, in this case oriented vertically, only the vertical components of the electric field get through, reducing the intensity to I1 equals I0 divided by 2. Again, assuming half the light vibrates vertically and half horizontally, which is most of the case with unpolarized light. In a stream of unpolarized light, which again is countless EM waves, the average alignment percentage of horizontal and vertical will almost always be half and half because we get it from the sun and that thing's shooting off things like crazy. So for the second polarizer, which is now horizontal, according to Malice's law, in this case theta is 90 degrees, the intensity becomes 0. No light gets through because the cosine of 90 degrees is 0. Now, take a second and notice that our equation here for Malice's law for determining the intensity of light through these polarizers is the same equation that we used earlier to calculate the area of a projected plane. Let's add in now our third polarizer. We have the first one, the second one's 45 degrees from the first one, the next one's 45 degrees. And what's basically happening here is that instead of blocking the light, the intensity of the light is simply being taken down at each step based on this equation. So half the intensity from the first polarizer is halved again at the second one and is halved again at the last one. But as you can see, for each polarizer, we are just stacking our projected plane equation from the beginning. The bottom line here is that there is no probability about this. There's no kind of a quantum randomness, except for the fact that from the first beam of light, we don't know what percentage is what polarized. It's simply taking two vectors and calculating the remainder vector of motion visualized here. The reason 3 polarizers at 45 degrees allows more light through than 2 at 90 degrees is because the entire plane of the EM wave is getting reduced as it passes through each polarizer. The angle the electron's dipole moment is misaligned to the angle of oscillation of the EM wave reduces the plane experienced by the electron. The point here is that polarizers work the way they do because 1, light is a wave, not a particle. 2, only the part of the wave where the oscillation mostly matches the dipole moment of the electron is being detected as light interaction. And 3, because the motion of that wave over time produces a plane and we can calculate its effect on an electron via a projected plane. All right, now we're getting to one of my favorite applications of this. We are going to talk about nonlinear crystals. Now, to be clear, this is more of an observation than an experiment, but nonlinear crystals have baffled physicists. In a nutshell, here's what they are and why they're called nonlinear. We think light is linear because we think it's a particle. So light should go in a straight line. The problem with nonlinear crystals is there are certain crystals we find that when we shoot light through them, they can produce a split beam. And the craziest part about this split beam of light is that each split has half the frequency of the original light that we sent through it. Now, sometimes it's not perfectly half and half. Sometimes it's 30%, 70%, things like that. But the point is, it is taking the original frequency of the light that we shot through the nonlinear crystal, and it is not only splitting it into two other beams, but it is distributing the frequency total between them. There has not been a good explanation for why this happens. But now that you know that when we have a single electron and light interaction, that we get a ring of potential photons, the explanation for how nonlinear crystals works becomes perfectly clear. So what makes nonlinear crystals special is that they have an incredibly uniform and symmetrical molecular structure, which allows for this very unlikely arrangement to occur where two electrons are equal distance from an emitting electron. So you can have an electron stimulated by a light wave oscillate, producing its electromagnetic wave, and that expanding ring hits two electrons at the same time. And that is how we get this reaction where you have two split beams of light. The reason the frequency is cut in half is because you have two electrons responding to the change in the electric field at the same time. If I were to take a certain amount of force and push a heavy box, that box will move at a certain speed. But if I take that same amount of force and I push two boxes now, both of the same original weight, they're both going to move at half speed. And this is why the frequency lowers, because since we have two electrons and they're both kind of rebalancing the field as they move, it takes away from the acceleration, causing the frequencies to diminish, and they diminish equally. Again, it doesn't have to be 50-50. The point is it's diminishing, basically distributed across the two electrons, both equally in the original frequency. This is an incredibly classical, intuitive, and easy to understand explanation for something that we have never had a good explanation before. Up until now, one of the most popular explanations for why this happens, and I don't even think I could perfectly describe it, but it's basically blah, 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 vacuum energy effects. Just so you guys know, vacuum energy, which does exist, but it's kind of the quantum electrodynamics version of the underpants gnomes.
You see, phase 1, collect underpants. Phase 2, phase 3, profit. Oh, I get it.
It's just kind of a general, we saw something weird, that's how we're going to explain it. So another part of this explanation that I've been giving you about what light really is, that nonlinear crystals really drives home, is this idea of light as a lottery. That a lot of the interactions we observe are often a certain amount connecting from one electron to another and a certain amount missing. When we observe light through a nonlinear crystal, it is not all the light that gets split. It is a small percentage of that light. In some cases, as low as like 1 in 150,000. And that just really drives home the fact that even in a nonlinear crystal, where you have a uniform and symmetrical molecular structure, the chance for a photon ring to be observed as a ring and actually stimulate two electrons at the same time is still incredibly low probability. So it explains why this reality mathematically has existed in front of us for a while now, but we've just seldom ever observed it. But nonlinear crystals show that we have observed it. All right, now, there are rabbit holes here, okay, that I tremendously appreciate. And I hope that maybe this thought inspires some other optic engineers and optic researchers to dive down this rabbit hole even further. But sadly, I got to move on. But again, I just can't stress enough how the nonlinear crystal interaction has been showing this whole reality right in front of our faces. We just never had a good understanding to explain it and know what was going on. Okay, let's move on to the showstopper, quantum mechanics. So when talking about quantum mechanics, what do we mean? For most people, including fans of the Marvel Universe, what most people think of when they think of quantum is just very small and maybe bad CGI. But the term quanta was meant to refer to small, discrete amounts. It's where we get the Planck length that we've been referring to earlier in the video. And it basically means this idea that there's the smallest possible unit that we can measure and observe this world through. Over time, however, quantum mechanics has grown to incorporate some rather dubious, strange, and fantastical ideas that physicists are still clinging to for dear life, and I want to start cleaning that up. So when we're talking about quantum mechanics, here's some of the main concepts we're talking about. Number one, discrete energy. We just talked about that. In quantum mechanics, energy is communicated and works through discrete quanta. This one I'm actually fine with for now. So we're not going to mess with that one. That's fine. You can keep that. Number two is duality. So that's what we've been tackling through this whole video. The idea that photons and other subatomic particles are basically both waves and particles, and depending on the experiment, sometimes it's wave, sometimes it's particle. So that one, obviously I have a big problem with. That's kind of the point of the whole video. So number three is probabilistic nature. And underneath that, we kind of have two main things. We have the wave equation and we have superposition. And these are two that get talked about ad nauseum. So the wave function is a mathematical tool that is representing a statistical probability distribution of where we might find a particle in any given situation. And superposition refers to this idea that a particle exists in more than one state, often referred to as spin or polarization, at a time until it is detected. And we're definitely going to talk about that a lot. Number four is entanglement. Now, we might argue that entanglement in many ways is the same thing as superposition, but I'm mentioning it as a standalone concept here because it is a persistent interpretation of superposition. And it is the thing that it probably draws the most mystery and, crazy ideas and all the things that we're just bothered by when we talk about quantum mechanics. Entanglement is the idea that by measuring the superposition of one particle, an entangled particle will now be affected when we measure its superposition. That's the idea behind entanglement. It's the idea that there is some information being communicated through space faster than light, and that these two particles that are entangled, meaning they either have opposite spin or opposite polarization, can affect each other instantaneously when we measure it. And that is a big problem. So now that you understand this model I've presented for the photon as just a word we've given to an interaction, and now that we've gone through all the experiments, let's apply the consequences of these things to these concepts in quantum mechanics. Number one, discrete energy. As I said, we're fine with that for now. We're just going to leave that alone. Least problematic of all the different concepts here. Moving on. All right, so duality. Let's talk about that. Well, that's what this entire video has been about. There is no need for duality. It's a wave. A photon's a wave. It's not a particle at all. However, there are geometric conditions that exist that will produce point-like interactions. So at least for the photon, we don't need duality at all. No more mystery. As a matter of fact, eliminating the duality, as we showed with nonlinear crystals, clears up a lot of issues with how photons work. But I'm only mentioning this again because I do want to draw a line and say, no, there's no duality with a photon. I haven't talked about what an electron really is. I haven't talked about any of the other particles in the standard model. There is, and we will discuss in a later video, a difference. There is a line that is crossed from a photon to other things. So for now, I just want to say we don't need duality with a photon, but that already changes a lot. I believe you will find that even when we cross the line into other particles and other parts of the standard model, there are similar explanations. Number 3, probabilistic nature. So this is one that is honestly still debated. There's still lots of people who do look at the wave equation and say, this is just a math tool. It's just something we're using to manage the fact that it's very difficult to measure these very small things. And because they move around a lot, there's a certain probability of detecting them in different places. Fine. But the madness around this idea of wave function collapse, that the wave function disappears when we detect a particle, and in the case of a photon, when we detect an interaction. First of all, nothing is collapsing. We made up the wave equation. It's not reality. It is a tool we are using to cope with an imprecise way of dealing with reality that we have. And that's it. So we don't have to have any mystical or metaphysical things to handle that. But also, I hope you've learned through the course of this video that when you see these experiments on photons and light talked about on YouTube or in science books or in these other things, I hope that you can now be vigilant to see how lazy they are about distinguishing between observing a single electron interaction with light and a stream of electron interactions with light, or a coherent light wave. And this failure to distinguish between the behavior that we observe from coherent light with what light really is at that singular level is one of the laziest and one of the most destructive things that we have done in our conversations about quantum mechanics. Okay, now what about superposition? Much the same thing can be said about superposition. Saying that light or a particle can be in one of two positions until we measure it just simply means physically it could be either. It's like flipping a coin. I don't know which side is up until I measure it. Again, it's mysticism we are inserting into the math when the math is simply a way of managing uncertainty. But the thing that has made people take superposition to this next level of magic is the idea of entanglement. So we are going to spend the majority of this time and the rest of this talking about entanglement. The most important thing to realize is that we call photons entangled when their polarization is correlated. And that can mean both that we have two photons with the same polarization, or we have two photons with opposite polarization. One of the things that's just interesting with photons versus all the others is, when we're talking about entangled electrons, they have to be opposite. But with photons, we often call them entangled when they're the same or when they're opposite. And the reason we do this with photons is because it depends on how we quote unquote entangled them, and it depends on the nature of the experiment itself. And whether or not two photons have the same or opposite polarization is something we likely already know based on how we constructed the experiment. So you might be asking yourself, that doesn't sound so spooky. What's the big deal with entanglement then?
That is an excellent question.
Adding to this, you need to understand that polarization is relative. Going back to the card here. That's right. There's nothing inherent to the nature of a polarized photon. The photon is polarized horizontally if it looks like this to me, or to you, or to however we observe it. It's polarized vertically if it's aligned like this to you or me. So what that means is to change the polarization of a photon, all I need to do is change how I measure it. So if polarization is not an inherent property of the photon anyway, why do we think it is so significant when we talk about entanglement?
That is an excellent question.
So if polarization is relative, and how we determine that photons are entangled is with polarization, that leads to the question, are photons entangled at all? I say no. That's right. When it comes to photon entanglement, it's just more mathic. Whoa, wait. Don't do that now. We'll ruin an entire video with a copyright strike. Let's do that as a follow-up video.
Oh, fine.
A photon is mathical and entanglement is pure mathic. I am introducing this word mathic to mean any time we take a mathematical equation that simply allows us to describe our observations and instead add a whole bunch of mythos and extra interpretation to then imply something weird with reality. I hope you like it. My wife thought of it. The reason we thought photons were entangled to begin with is because of our experiments with polarizers, which we covered earlier. Now, the difference between the experiment we went through and the experiments that they often use to show that photons are entangled is that with ours, we were stacking the polarizers one after another. But in these entanglement experiments, they often take the polarizers and spread them out, sending the light from the first polarizer now to two other polarizers. So I don't get accused of misrepresentation. Let me take a second and play the description for this in the words of YouTube's most respected science communicators.
So we haven't proved hidden variable theories are impossible, just that any hidden variable theory would have to have the interaction between the particle and one filter affect the interaction of the particle with other filters. We can, however, rig up an experiment where the interactions cannot affect each other without faster than light communication, but where the same impossible numerical weirdness persists. The key is to make photons pass not through filters at different points in time, but at different points in space at the same time. And for this, you need entanglement. For this video, what we'll mean when we say two photons are entangled is that if you were to pass each one of them through filters oriented the same way, either both pass through or both get blocked. That is, they behave the same way when measured along the same axis. And this correlated behavior persists no matter how far away the photons and filters are from each other, even if there's no way for one photon to influence the other. Unless somehow it did so faster than the speed of light, but that would be crazy.
Now, if you have been really grokking this video, you might have already caught the problem. As these assertions of entanglement are based on the same misconception, there is a certain percentage of particles passing through the polarizers. There are two problems with that statement. The first is the word particles, and the second is the word passing through. For the first, we have just spent this entire video showing that a photon is not a particle. It is just a wave. There's no really photon there. It's just a word we give to an interaction. Can't say it enough.
You can definitely say it too much.
Okay. The second problem is the term pass through. The reality is that 0 photons pass through a polarizer. As we mentioned earlier with the double-slit experiment, anytime you stimulate an electron, you are creating a new EM wave. When the light hits the polarizer, nothing passes through. There is just a certain percentage of the energy that is converted to new light waves, and the rest is converted to heat. Side note, for the real technical out there, actually EM waves never stop, they're just canceled out. If that's bothering anyone, we'll cover it in a follow-up video.
And if it's bothering that individual, they understand this well enough that they can probably move on to the next video.
I would agree with you there. In other words, all the assertions of entanglement rely on the assumption of the probability of particles passing through a filter, when what's really going on is just the conversion of a projected plane based on the oscillation of the wave and the dipole moment of the electron. Bell's theorem, shown here, is a simple probability statement that requires particles in an absolute state. The X, Y, and Z are three options for spin, up, down, horizontal, not really a state, but in between. P is the probability of any of those two measured states matching. We don't need to break down the math for our purposes here, and there are other resources to do that. I'll link below if you really want to understand it. But the obvious flaw here is the equation itself, that the percentage of intensity of light is being reinterpreted as a percentage of particles passing through, again, a filter based on spin, rather than a product of the vectors which determines the amplitude of light resulting from the interactions of the EM wave and the electron dipole moment. Because of this, it makes sense that our measurements are consistent across vast distances of entangled light. If two wave sources have the same or opposite polarization, then their detections will either be the same or inverse relationships of Malice's law, which we've gone through. Said another way, we have been using the math of a coin sorting machine to imply a spooky relationship between two cards being tossed through slits. The particle nature of light is the false assumption that was piled on top of with further nonsense. In reality, all these entanglement experiments with light had to have such a spooky explanation because we couldn't just admit we were wrong about the particle in the first place. So I just want everyone to let that sink in for a minute. This equation, Bell's theorem, and yes, there have been experiments showing that the equation, is consistent. We had an entanglement experiment win the Nobel Prize. So I realize you're taking the word of a random jackass YouTuber over a Nobel Prize winner, but Nobel Prize winners have been wrong before. It doesn't matter that this equation works, because all this equation does is tell you what it think wouldn't happen if there were hidden variables in two particles. It doesn't really predict what would happen. And that's the first logical fallacy, and I can't believe it's made it that far. But again, it's not even about fixing the equation. It's a statistical equation. When we know what's going on, you don't use statistics. I talked to a statistician about that because I wondered if, maybe we can just fix Bell's theorem. No, we can't, because it's statistical. Once you understand light, the real equation is just Malice's law. That's it. It's just we've never interpreted Malice's law to be what's really going on. We've always thought there was, some other spooky explanation behind it, when in fact it's just literally describing what's going on.
But wait, Chris, if photon entanglement is bogus, isn't that what's going on with quantum computers? Don't they use entangled photons?
That's right. What is going on with those quantum computers anyway? Weren't they supposed to change the world and destroy the internet already? How are they coming? Look, behind all those mythical explanations of quantum computers, it just comes down to the fact that we've created a mechanism to juggle a 1 and a 0 until we need to measure it. This is only useful for very specific calculations, and I'm not diminishing the fact that it's a very useful technique for solving very specific calculations. They have shown the ability to do that. However, it doesn't even require entangled photons to achieve. We could use other mechanical processes to do the same thing, and we have. In fact, many quantum calculations have been proven possible to be done just as efficiently by non-quantum computers. Now, I'll stop there, because the only reason I can get away with saying this is because I'm just a random crazy person on YouTube with a small following. But for me personally, I will not be investing in any quantum computer companies. So let's wrap this up. In conclusion, I believe the evidence is extremely clear. I have provided not just a breakdown of all the weird experiments that got us into this problem to begin with, but I have provided a few ideas for some further verification of what I'm saying can be shown to be true. There are no particles here when we're talking about light. There are just interactions, and the point-like nature of it just has to do with how many conditions are required for those point-like interactions to occur. And depending on how you look at those interactions, sometimes they are confined to what we would call a rectangle. And when we're looking at the actual potential for those interactions from a single electron, we have a ring contained around in the middle of a sphere. But let's talk about why this matters. I don't know about you, but for me, I just like having a consistent and intuitive theory that explains all these experiments and observations without any of the weird and very overused sci-fi plot tropes. More so, it matters because, as I said at the beginning, Our theories around the photon formed our foundation of quantum mechanics. And while I admit there is nothing particularly earth-shattering about what I presented here, by using this as a foundation, you will see in future videos that I can now build off of this to create a whole new approach to subatomic interactions. This simple geometry of what's really going on when we are talking about light gives us a pathway to reinterpret the exchange of energy into equations that are nothing more than distance and relative acceleration. That's where we're going. All right, but Chris, what about extra dimensions? So I started this series talking about extra dimensions, and I did. And we didn't talk about any extra dimensions in this video, and that, again, because I had to clean up the ones that we have. But as we get into the next video and we start talking about the M in EM, this becomes, again, a solid, intuitive foundation for us to build the logic for the rest on top of. So I hope you will forgive me for having a video that may be less sexy, but I hope more useful. So fear not, the next video, it's going to be a doozy. So all good theories need to be falsifiable and provable. Well, here's the thing. If we were starting in the late 1800s and we didn't have all this plaque built up around our thinking, then all the experiments we covered today are pretty good evidence to prove this theory. And I've even added a little more when talking about nonlinear crystals. But if we need even further evidence, the best experiment would be if we could suspend a single electron in the middle of a ring of detectors. Then we could oscillate the electron at a light detectable frequency and see if different detectors are activated at different times. And if you are a regular viewer of this channel, all two of you, thank you very much, you will notice that's very similar to the light compass idea. Okay, but is this falsifiable? Sure, I'll tell you what you can do real quick to falsify this whole idea. Suspend a photon. Go ahead, just do it. We can suspend an electron, we can hold an electron, we can caress it, we can cuddle it, we can keep it in a box. But we can't do that with a photon because it's always moving, because it's a wave. If you really think that a photon is a particle, just show me an experiment suspending that photon still in space, and everything I said is complete hogwash. Is this theory comparable? Meaning, how does this stack up to other theories of light? Well, let's just take a minute and look at the scoreboard. Probabilistic wave function collapse. The idea that light just exists as wave until we detect it, and then the whole thing collapses and observation creates reality. Come on! We have the many worlds or multiverse theory. And while I know that that theory is fun and makes for very mediocre movies, except this one's good. It is absolutely absurd that we have had to insert multiple universes just to explain this. All of the observations we have had about light taking up every possible path at once until we measure it can be easily explained by the fact that, again, a single instance of electron generating EM wave is a ring, and the fact that often when we are observing light, it is as a coherent stream. That's all we need. We don't need Earth 612. We also have pilot wave theory, which admittedly is one I have drawn a lot of inspiration from, and when I was getting into physics, it really fascinated me. And I think that pilot wave theory is one of those that I am grateful for, because at least it was driven by some logic and deduction. But we don't need pilot wave theory with light. We don't need a wave carrying a corpuscle, or that's what they call a little particle, along. We don't need that with light. We'll talk about that a little more with electrons. So where do we go from here? I want to take a minute and clarify what this theory does not do. It does not disqualify or disprove current thinking on quantum mechanics or entanglement altogether. A photon is just one square on the standard model bingo chart. It does go a long way to call in a lot of our assumptions and our interpretations into question, But until I cover these principles in the context of actual particles, which an electron is, we will not have unraveled the whole problem. The convenient part of focusing on light is that most of our interactions with light only take up the E in EM. I was able to ignore the magnetic component completely for this entire presentation. So the next essential step is covering and creating a similar, intuitive, and easy to understand explanation for magnetism. I also want to acknowledge that there's a lot of nuance to everything I covered and a ton of rabbit holes. Every experiment I covered here could take up an entire video. And Lord knows my editor knows that I have been tempted to do so. There is also a whole world to explore specifically for the ramifications for nonlinear optics. I can only hope I inspire some people to maybe take some of the ideas and run with it. I am almost certain this video will need a follow-up to still patch some things or clarify some things, so I'm definitely going to do that as needed. I never know which aspects of these videos are going to be the most problematic or the most confusing. This video I have gone over with more people than probably any other, like I said, including people that are actually experts in this field. But as we open up to the broader audience, it's just hard to know. And most of them have been with me the whole time, so they're used to it all anyway. So please keep your eye out in the description, as I will post clarifications or corrections or other things as comments come in. At the least, I hope you appreciate and find value in having a consistent, intuitive, and practical framework for light. I encourage you to go back to your YouTube feed or however your research rabbit hole or however you best approach this material and look up all the other videos, papers on light and photons. I believe you will see this framework holds up and offers better answers than anything else out there.
It's a wave.
It's a wave with geometric conditions for interaction.
It's a wave.
Okay. Finally, I want to say that during my series, I have argued against many fun and popular ideas. Entanglement's a fun idea. Multiverses are a fun idea. I've shown that time travel is impossible. I'm resolving wave-particle duality, and I've punched a hole in entanglement. It seems like I'm just sitting here trying to kill off everything fun and sexy about theoretical physics. All I can say is that we have to get rid of and move on from our old toys before we get new ones. And let me promise you, I have new toys to play with. Please keep your eye out. Based on the comments I get in, I will be doing a follow-up live session Q&A. It'll be the first time I do that. And in the live session Q&A, I will also talk about other things like expanding into Patreon or other means. I don't know yet whether I'm going to do the live Q&A or a follow-up video first. I need to give this a minute to simmer and see what the reaction is. So that is going to happen. Please keep your eye out for that. As always, I appreciate the encouragement that all of you have given me and pushed me forward. This is very, very difficult. It's tons of work. Emotionally, it's difficult because I am well aware of the hubris of the whole thing. Nevertheless, I'm very excited about where this is going. I hope you're excited too. And thank you as always for the time. Also, anything you can do to help this grow, share, like, and subscribe. Most of all, leaving this playing in the background to increase the watch time while you're doing other things like chores around the house is actually probably one of the most effective things you can do to help the video rank on the YouTube algorithms. This video took a year of work. The next video will probably take even longer. This takes a lot of research, it takes a lot of validation, checking work, it takes a lot of animation work. Thank you. In the meantime, obviously, as I did before, I'm going to take a break, do some other topics in the meantime that are easier to work on. I have some other things I'm passionate about. And I just ask everyone to keep an open mind and please try out some of the other videos that I'm doing. I'm very proud of those too. So I just want to say once again, thank you, many of you, for your support. I look forward to hearing from all of you, even the trolls. And until next time, everyone, sleep well and keep learning.
That is an excellent question.